Oh, wait, you're listening?
Okay.
All right.
Okay.
All right.
You're listening to Radiolab.
Radiolab.
From
WNYC.
See?
Yep.
I'm Latif Nasser. This is Radiolab, and today
Hello.
we are following the internal compass of our senior producer, Annie McEwen.
All right. So last October, I traveled to a mountain in Pennsylvania. It's dusk. It's a place called Hawk Mountain Sanctuary.
Hey, how are you?
And I was there to join a group of volunteer researchers to wait in the cold and the dark,
Get our gear organized.
hoping to catch some owls.
Okay.
Catch some owls?
Yes, but not just any owls. These were northern saw-whet owls. Do you know what a saw-whet owl is?
No.
What is the deal with these birds?
So I'm going to be dryly scientific here and describe northern saw-whet owls as cosmically cute birds.
Okay.
Because they are.
So Scott Weidensaul here, he's a natural history author. He was actually the guy that invited me up to come see these owls.
They're the smallest owl in the East.
They're about the size of a soda can.
And do you ever just take one and put it in your pocket?
We're not allowed.
Okay. They're like kittens. They're kittens, but they're owls. They have these huge eyes.
They weigh a little bit more than a robin.
And to catch them,
Oh, this net is so thin.
Hopefully they won't see it.
you have to string these wispy black nets up in the woods.
Fire it up. Watch your ears.
You set up speakers and you blast this sound.
What is that?
That is a recording of a mating call of a male saw-whet owl.
Sounds like a truck backing up.
It's the sexy sound of love if you're a female saw-whet owl.
They're romantic.
Anyway, so you get all that stuff set up, you walk away from the net, you hunker down, and
You just
wait.
hang out, like play cards and stuff?
Yep.
And why are they trying to catch these owls?
Well, they're migrating owls, so if they can tag them,
We can find out how long these birds live, where they travel. Do they come back to the same place every year? Do they have the same mate every year? Do they go to the same place in the winter?
it's like they get this window into the bird's life, which is great and cool. But actually, the reason I was there that night was because I had recently become really obsessed with a very particular part of a bird's body.
What part? What's the part?
I will tell you in a minute.
Okay.
But anyway, so we got the net set up, and then after sitting around for a whole hour,
Are you going up? We're going up?
Let's see what's.
Oh my gosh.
we went to check the nets. And in the first hour,
Looks like no owls in the nets.
there were no owls.
So don't be discouraged.
Not at all.
We didn't catch anything in the first net check last night, and then we had a very busy night.
And in the second hour,
Okay, second time looking at the nets.
there were
No owls again. No.
Does WNYC have a reputation for being a jinx?
Oh no, you think that's what? No.
And at some point in the night, we had been joined by this group of kids, this young birders club, and they were so excited to see owls, and they were being amazing sports. But, it was past their bedtime. It was getting colder and colder.
Stars are coming out.
Like the wind was picking up, and these nets were just so empty.
Oh, man.
And I started to have this thought like, man, we are just sitting in the woods listening to a garbage truck backing up, and owls are not coming.
It's about 9 o'clock at night.
But then on the third hour,
Checking the nets again. Third time. Phew. I think there might be one. There's one.
owls.
There's an owl. Wow.
There's two of them.
In the glow of my headlamp, I could see these two tiny bundles of brownish white feathers caught out of the air like fish in a net.
Oh, I can see its yellow eye. Wow.
Got him.
The volunteers detangled them from the nets
Come on, open up your little talon.
and brought them down to the kids.
She's looking at me.
And they watched as they were weighed and measured.
And we put a little leg band with a 9-digit unique serial number on their leg.
He's really feisty.
And then Scott did this very surprising thing.
I'm going to lift the the facial disc away here.
Like, you know, they have these disc faces?
Yeah?
Scott gently lifted forwards one side of the owl's face.
And you can actually see that ear opening.
And it reveals this crazy inner head world of the owl.
What is in there?
It was like this surprisingly deep ear hole. It had this sort of like inner cave thing, all these nooks and crannies, and it was all covered with like a very thin layer of pinkish skin.
Oh.
But the wildest part was that
That gray thing you see is actually the back of the eyeball. And that
you can see the back of the huge bulging eyeball in its head. Like, you see it.
It's a little trapdoor to the back of the eyeball, almost.
Yeah, pretty much.
Oh my God.
I couldn't believe it.
Why would their face open like a door?
I don't know, but it was amazing and it was so weird. And like, I was so excited that we got to see this owl's eyeball, like so much of it.
Wow, that was the coolest thing I've ever seen.
Because, like, that's kind of the whole reason I was there, to take a good look at the eye of a bird.
Okay.
How come?
Because I had recently learned that it's possible that one of the biggest biological mysteries of all time, this fleshy, feathery animal mystery, could be answered finally by tapping into the most abstract, far out there, hidden realm of the universe.
All I can see is yellow eye.
A place where the laws of space and time are completely upended. And that all of that is somehow happening somewhere inside
She's glaring.
the eye of a migrating bird.
Okay, I have no idea what you're talking about,
Okay,
but I would like to.
great. I was hoping you would. So before we go totally sci-fi, I'm just going to do a quick little orientation of things.
Okay.
So, as you know, many birds migrate.
Right.
Twice a year,
this enormous avian river is passing overhead, just stitching the continents, stitching the hemispheres together as they have been doing for millions of years.
And the big biological mystery that humans have puzzled over for millennia, and something we've actually talked about at Radiolab before a couple of times, is basically just, how do they do it?
Like, how do they figure out where to go?
Yeah, like, how does a little migratory bird leave its nest, say in Alaska, and without compass or map, manage to arrive on the same branch of the same tree in a backyard in New Zealand year after year after year?
Yeah. Right.
And we don't know how it does that?
Well, we know pieces of the answer. So birds actually use a bunch of different things to orient themselves. Like they use the stars, the sun, they follow mountain ranges and rivers, they use their sense of smell, and sort of incredibly, they can also use their sense of hearing.
birds can hear extremely low-frequency sound waves that are generated by ocean surf and tectonic activity and wind blowing through high mountain passes. And there's been some speculation that a bird migrating south through the Great Plains of North America would be able to hear the Atlantic Ocean in one ear, the Pacific Ocean in its other ear, and the rumble of volcanoes in the transvolcanic belt across the middle of Mexico dead ahead of it.
Wow.
So they have all these tricks, but the thing is, if you take all that stuff away, birds can still do it. They can still orient themselves in space, they can still figure out where to go. So there's like something else at work here.
Like magnetic fields or something?
Yes. So
Since the late 19th century,
biologists have thought that birds probably do use the Earth's magnetic field, which is this absolutely massive force field that surrounds the planet like a huge bubble, protecting it from the sun's solar winds.
Right.
But the weird thing, and part of the thing that's been stumping scientists all these years, is that
an organism really shouldn't be able to sense it.
Huh. Why not?
because as humongous and important as it is like weirdly weak.
It is really, 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 really weak.
Really?
Yeah, it's like 10 to 100 times weaker than a fridge magnet.
Wow.
And so, like, the question is just how do they sense this super weak thing? And for a long time, the assumption was that they were using crystals.
These tiny little deposits of magnetic crystals called magnetite in the beak of the bird.
And that was a story that we talked about in our other Radiolab episodes about this mystery.
And presumably this acts like a little magnet.
And therefore a compass?
Pulls the beak to the north or something.
Yeah, that's what I thought happened.
Yeah, but the problem is, like, magnetite doesn't seem to be connected to the bird's brain in any way.
Huh.
So even if those deposits are sensing the Earth's field, there's no message getting to the brain of the bird for the bird to then say, that's north, I should turn this way, da-da-da-da-da.
Huh.
So it seemed like birds must be using the magnetic field to find their way around, but like nobody could figure out how they could sense it. And this is where the mystery of how birds do what they do has just been stuck for many, many years.
Okay.
But now we get to the new crazy, amazing, maybe we figured it all out part.
Right.
Emphasis on crazy maybe.
This is where we go seriously off the rails into the deep sci-fi sounding stuff. So
the story of the deep sci-fi sounding stuff actually starts
in the 1970s
with a guy named Klaus.
A young German physicist named Klaus Schulten, who was thinking about the problem of magnetoreception in birds. And
at the time, biologists were like all about these little iron crystals in the birds' beaks. But Schulten,
he didn't buy this,
was thinking about some very strange physics.
What's called a radical pair.
A radical pear.
What is a radical pear?
I mean, I think it's a piece of fruit that just has red Karl Marx. A radical pear. It's like Animal Farm, but for plants.
No. So this is like an actual pair of things. Okay. And the things that are paired are electrons. And that means that we have to take a moment here to dig into how things work down at the teeny tiny scale of itty bitty stuff.
All right. We're zooming in or we're diving into
We're diving and zooming.
Diving and zooming.
Here we go. Down into the land of the teeny tiny electrons and protons and photons and neutrons, all that stuff. And maybe you've heard some things about this tiny world, and that things get very weird down there.
Yeah.
Right. So this is the quantum world.
Right.
So the tiny things down in the quantum world, it's like they break all our normal rules of space and time. For example, one thing can be in two different places at the same time. Things can move through solid barriers. Effects can happen before causes.
It's really weird.
Yeah, like, and if this were true, like in the big stuff world, it would kind of be like you catching a ball could actually cause me to throw it to you.
What?
Or the ball is both in your hands and my hands at the same time.
Okay.
Or it's, both blue and green at the same time.
Whenever I hear about this kind of thing, it's always kind of incredible, but it's like also incredible. Like you can't even, it doesn't even seem real. You can't even believe it.
Totally. Yeah. And I think it's like we've just never experienced anything like this. But this is what hard-hitting physicists, people who have studied this stuff all their lives, they swear this is true. These are just the facts of life down there.
Yeah.
And as weird as it sounds, there is one of these little quantum facts of life that Klaus thought might somehow help birds see the magnetic field.
Yeah. Schulten had the idea that it was tied to an aspect of quantum physics known as quantum entanglement, where, oh boy, and now you're going to expect me to explain something in quantum physics.
So like super simple version is that sometimes two particles can become linked in a particular way such that
what affects one will instantaneously affect the other. And
like you can tweak one of them and the other will react right away, even if those particles are really, really far apart.
At opposite ends of the universe.
Okay.
Which is, just another way that tiny things break the classical rules of space and time. Because, in our world, the only way for one thing to affect another is by sending some kind of signal through space, which takes time. But it's like these two particles have some kind of backdoor space-time loophole.
Yeah.
So they're just kind of insta-linked.
Right. That is weird.
Yeah. And this is what scientists call entanglement.
Got it.
And of course, this is totally fodder for sci-fi writers like imagining a world with teleportation.
Energize.
Or whatever.
It's exactly. It's beam me up Scotty stuff. No doubt about it.
But also, it's a real thing. I mean, it's the basis of quantum computing.
Right.
Part of what makes quantum computers so powerful. Anyway, so back to Klaus Schulten. He's sitting back there in the 70s thinking about a particular kind of entangled particles called radical pairs.
Not the fruit.
No, right. So if you picture an atom in your high school textbook.
Uh-huh.
Picture it?
Yeah.
It has a nucleus with electrons zipping around it.
Right.
And a lot of times those electrons come in pairs. Now, to understand that, there is one thing you need to know about electrons, which is that they have this something called spin. Now, apparently they're not actually spinning, but this is how physicists talk about it, as if they can spin in one direction or the other. And when you have these electron pairs, their spins are linked. Now, Schulten knew it was possible for a photon of light to knock one of those two paired electrons pew, off its atom, away from its partner, and if it happens to land on a neighboring atom, even though they are now physically separate, the electrons stay paired. They are still connected. So now those two atoms become a radical pair. They're spiritually one, in a sense, because they have these electrons that are entangled in this spooky, instantaneous quantum way.
Okay.
So all of this was just total stock and trade quantum mechanics at the time. But Schulten, doing some elaborate experiments with radical pairs in the lab, had noticed something he didn't expect. When these atoms become radical pairs, they are suddenly super duper magnetically sensitive.
Okay, so now I'm seeing the bird connection here. Okay.
Yes.
Yep.
Okay, so and Schulten, he had buddies in biology land, and he was well aware of this whole how does a bird sense the magnetic field mystery. And so he thought, hey, maybe if there are radical pairs somewhere inside the bird, maybe these could act like a magnetic compass.
And so Klaus Schulten came up with this idea and submitted it for publication, wrote it up in a paper, submitted it into publication to an American physics journal, and it was rejected. He got a rejection letter saying that a less bold researcher would have consigned this idea to the wastebasket.
Whoa.
Yeah, I mean...
He did eventually publish it in a small German journal, but...
Even then, it was mostly ignored.
Why did it get rejected and then ignored?
I think for physicists, on the physics side, all this quantum stuff, it's very fragile. As soon as there are a lot of things bumping around and into each other, these quantum effects, like entanglement, they disappear and just collapse back into normal. And this is why Google and Microsoft, whatever, have spent a buttload of money keeping their quantum computers really, really cold.
Right.
And inside special things, because they need to keep things very, very calm in there. Yeah. Otherwise, molecules are just going to bump around and ruin everything. And the inside of a bird, or really any animal, is a very busy, bumpy place to be. So Klaus Schulten, saying that entangled pairs of electrons might help a bird sense the magnetic field, that was kind of insane.
This was very difficult for many physicists to accept for a long time.
As for biologists...
Can you turn the volume on me down? Yeah. People think I'm too loud.
Especially excitable biologists.
When I get excited about something, I may be even louder.
Like Henrik Mouristen, who works at Oldenburg University in Germany.
Yeah, now they are good.
They honestly just could not understand the math.
My God, there is no way with my mathematical knowledge at that time or now, for that matter, can read that paper.
Wow.
So this is extremely hard quantum mechanics. I just gave up reading the paper, honestly. So
okay, so you found this paper and you're like, never mind, I can't understand.
I could not, imagine any experiments or anything because I didn't understand it well enough.
Got it. So Schulten's paper and his idea just sits on the shelf, collecting dust. But lucky for us, much like the quantum world, here on the radio, we have the ability to warp space and time. And so we're going to take a little break. It's going to be 1 minute.
Okay.
And in that 1 minute, 22 years will have passed. And we will arrive at a moment where this quantum bird theory will again take flight.
Okay. So listener, stay entangled with us. We'll be right back after this. I'm Latif Nasser. This is Radiolab. We are back from break with producer Annie McEwen. And all together, we have just made a quantum leap forward in time.
Yay.
How many years? 20 some odd years? Something like that?
22 years. Yep. Okay, so Klaus Schulten, in that time, Klaus Schulten has moved on to other things. He became a very important biophysicist. And for the most part, he set magnetoreception in birds aside. Until...
Year 2000, Schulten had a very smart graduate student called Thorsten Ritz.
And he, together with Schulten, they took that old paper from the 70s and...
wrote exactly the same hypothesis again, with illustrations and in a language that biologists could understand.
And they also added one really important thought, which is that they think this radical pairing thing could happen inside the eye. Because, of course, that's the place where light gets into a bird.
And then it took off like crazy.
Because now biologists knew where to look and what to look for. And in fact, thanks in part to Mouristen's work, we now know that there is a molecule.
It's a pigment protein that is found in the eyes of many birds, especially migratory birds,
that can do this radical pair thing when it's hit by a photon of light. And it's called cryptochrome.
A molecule that absorbs light and uses this light energy to move an electron.
And since then, scientists all over the world have done experiment after experiment, finding more and more supporting evidence.
Showing that this idea he had back in the 1970s was correct.
Okay.
So, can I play this out for you?
Yes, please.
Okay. Ready? Here we go.
I'm ready. Let's go.
Okay.
So here is the idea.
A bird is flying at night under a blanket of stars.
Mm-hmm.
And if we were to zoom into its eyeball, we'd see cryptochrome molecules made up of atoms with a bunch of paired electrons buzzing around them.
Yeah.
And these pairs, like I said before, their spins are linked. So they're like little spinning dance partners.
One up, one down.
One spins up, the other spins down.
Always.
Okay.
So there they are. They're just dancing in their little atom home together, and they're completely uninterested in the very, very weak magnetic field of the Earth. Until the bird glances up at the night sky, and then, bam!
The photon of light that was emitted 10 million years ago from a distant star
Hits the bird in the eyeball.
and it strikes this cryptochrome molecule, and it knocks an electron
Away from its dance partner, and it goes kapew! And it lands on another molecule in the eyeball.
That is a radical pair.
And remember, even though they're separated, they're still linked.
quantumly entangled.
So they're still doing their little dance, but now that they've been radicalized, they're in this
highly unstable state.
And they've become super duper sensitive.
10 million times more sensitive to Earth's magnetic field.
And it's almost like this giant presence that was lying hidden suddenly appears. And now their dance
is influenced by the magnetic field of the Earth.
So now, some of the time, they do their old up-down move, but they also sometimes spin in the same direction, like both up or both down or whatever.
Okay, so it's more variation, different kind of dance moves.
Exactly. Yeah, and like the key thing here is just like how much they spin opposite and how much they spin together. That changes depending on which direction the bird is flying.
Okay.
So for example, it could be like if the bird is flying north, those electrons are more likely to be spinning together, both up, up.
Okay.
And then let's say the bird veers right and heads due east. Now those electrons are more likely to be spinning opposite each other, up, down. Are you with me?
I'm with you. I think I'm with you.
Are you?
Yeah.
Okay, well, just to bring it home here, this is obviously incredibly simplified, but the important thing is that there are not just one, but millions of these radical pairs inside the eye of a bird, doing their various dances all at the same time as the bird flies along. And it's not like these little bits are acting like magnets, like pulling the bird one way or the other. Instead, you've got this kind of like Rube Goldberg bit of business at the end here, where different spins create different kinds of chemicals, all of that leading to the optic nerve sending electrical signals to the brain. Woo!
Now, this is very, very complicated.
Yes.
The uncomplicated part is really...
The bird now has a chemical compass in its brain.
And this chemical compass exists because the electron spin interacts with the Earth's magnetic field.
In other words, birds are finding their way around the planet, across hemispheres, thanks to these teeny tiny particles inside their eyeballs that are getting pushed around by this giant force field surrounding the planet.
And so you can do something with your eyes that owls can't. Bingo. Exactly. No owl will ever look out of the corner of its eye at you because they can't move their eyes. And that's one of the reasons, I think, why humans have always thought owls are wise, because they never give you any side eye. They only look straight at you.
On the mountain in Pennsylvania.
All right, we're going to let this bird go. I'm going to pass.
After we caught the owls and took some measurements and saw their eyeballs.
Everybody ready? Yeah. So I'm going to hold it up in my hand.
We let them go.
There he goes.
And now, most of the research on this quantum entanglement stuff has been done on songbirds, not owls per se. But the scientists I've talked to say that if all this is right, it's likely something that pretty much all migrating birds, including these owls, do. And so after learning all this, it was just this whole other thing, standing there and watching her fly off into the night.
On her way.
Especially in light of something that Henrik and his team discovered in 2005.
If you look into the brain of a bird and you ask, which part of the brain do you use to process magnetic compass information?
The answer is in the visual system.
It's seeing, basically, that is activated.
The bird is not only sensing the Earth's magnetic field, it's actually seeing it.
Cool.
Do we know anything about what it might look like?
Well, I mean, this could be some kind of shading on top of whatever else they're seeing. But in principle, we have no idea because we cannot ask the bird what it's seeing.
Right. So there's no way of...
No. I mean, birds are tetrachromatic, right? That means they already have a color channel more than us.
Oh, okay.
So they will see much more colorful world than we do.
Oh.
But it's hard for us to imagine how a much more colorful world would look like. You can go the other way. Humans have 3, but a lot of mammals only have 2. I can tell you that's a very, very dull world compared to the one we see. But a dog cannot imagine what our colorful world will look because it has never seen it and it will never see it.
Right.
So now you imagine, instead of 3 channels, birds have 4 channels.
Yes.
Then there comes on top that the birds have some oil droplets, which are basically filters, which means that they may actually have 6 color channels. How the hell 6 color channels look to anything, we have no idea because we can't see it. And then you add a magnetic channel on top, which also we have no idea how that would look. So it's guess. We will have to guess.
Okay. And when you lie in bed at night, imagining what this looks like, you basically limit yourself to some kind of shading and leave it at that? Or are you allowing your imagination to paint a stronger image?
I have a very scientific brain, so anything I haven't proven, I'm not going to fantasize about. So to me, I don't know how it looks like.
He's just not giving it to you.
He's not. No, he's not. Okay, so but I guess one thought I had was, but then I managed to say enough wrong things in a row.
No, that is impossible because all magnetic...
that I guess he felt compelled to help me out.
Okay, what it's most likely to be is some kind of landmark.
Whoa.
Like bright or dark spot, or blue spot, or whatever color we can't imagine spot.
And that whatever color we can't imagine is brighter when the bird is, say, facing...
towards north. And then it's gradually going to be darker away from that center.
So you could say like the color spot dims as the bird turns. And the spot is at its darkest when the bird is facing...
90 degrees to that.
Like at the east and west marks. And then if the bird keeps turning around...
will start getting brighter again.
Yeah, and is at its brightest again when the bird is facing south. So it's probably a gradation of a color that we will never see. But... we just don't know.
But it will not be at a specific distance. It will be more like 2 suns.
What?
Yeah, but don't now quote me for it being a sun. It can be anything.
No,
it can be...
No, of course.
But it's a spot.
No matter what it looks like. For me, I don't know. I guess I'm sort of envious of the bird. Like, there's this whole crazy part of our universe that is It's like a part of everything we are, but also we never get to experience. And, we can't even wrap our little brains around it. And yet these birds, it's like they get this direct visual experience, like a message from that hidden foreign realm.
Huh. Yeah.
And one thing that I found just kind of beautiful was that talking to Henrik over the phone recently, he told me that he thinks, and there's a lot of evidence to support this, that actually birds are only able to see the magnetic field at night. And he told me, if you actually watch a migratory bird after a day of eating or resting, a lot of them will fly to the tops of trees and you'll see them watching the sunset. And what they're actually doing is calibrating their compasses.
Whoa.
And as dusk falls, watching the Earth's magnetic field, in a sense, come online.
Whoa, that's so beautiful.
And then when they've got their magnetic compass set, they can take flight.
Going to look at a sunset the same way again. Thank you, Annie.
Thanks a lot, Tiff. And I have a lot of thanks to give for this episode. Thank you a million times to Rosy Tucker and the staff, especially Eric Snyder, Holly Merker, and Seth Benz at the Hog Island Audubon Camp. This place and these people are absolutely incredible. They let me come along with them to Monhegan Island in Maine to look for migratory birds, and I had a total blast. They have this amazing migration program in both the spring and the fall where you learn how to identify birds. You hike around this tiny magical island. You eat amazing food. It's just the best. I'm really trying to get my parents to go. Anyway, check them out at hogisland.audubon.org. Thank you also to the Ned Smith Center at Hawk Mountain Sanctuary and all the amazing owl tagging volunteers, Chris Bortz, Cassie Bortz, and Cheryl Faust, for putting up with me. Huge thank you to Jeremy Bloom, sound designer extraordinaire who helped me record the owls that night, and to my wonderful brother Jim, who for some reason agreed to spend his birthday helping me drive there and back again in one night. Huge thank you to Isabelle Andreesen at the University of Oldenburg for letting us use their beautiful recording studio for free, which was awesome. And finally, thank you to Andrew Farnsworth at the Cornell Lab of Ornithology, as well as Nick Halmagyi and Andrew Otto for helping me puzzle through the world of quantum physics in birds.
This episode was reported and produced by Annie McEwen, who also contributed original music and sound design. This episode was fact-checked by Natalie Middleton and edited by Becca Bressler, who was the steady hand that helped guide it where it needed to go. Thanks for listening, all you bird brains and radical pears. Until next time.
Hi, I'm Teddy, and I'm from Los Angeles, and here are the staff credits. Radiolab was created by Jad Abumrad and is edited by Soren Wheeler. Lulu Miller and Latif Nasser are our co-hosts. Dylan Keefe is our director of sound design. Our staff includes Simon Adler, Jeremy Bloom, Becca Bressler, W. Harry Fortuna, David Gable, Maria Paz Gutierrez, Sindhu Jnana Sambandam, Matt Keelty, Annie McEwen, Alex Neeson, Sarah Kari, Sarah Sandback, Anissa Vitsa, Ariane Wack, Pat Walters, and Molly Webster. Our fact checkers are Diane Kelly, Emily Krieger, and Natalie Middleton.
Hi, this is Beth from San Francisco. Leadership support for Radiolab science programming is provided by the Gordon and Betty Moore Foundation, Science Sandbox, a Simons Foundation initiative, and the John Templeton Foundation. Foundational support for Radiolab was provided by the Alfred P. Sloan Foundation.